Hey everybody. Today we're talking about conditional probability distributions. Here we're in a situation where we've got a couple of random variables, you can call them big X and big Y, and they have some joint probability distribution. And we're asking what happens to one of the variables, say X, when the other random variable, say Y, is fixed at some particular value. And we'll typically denote specific values of a random variable with lowercase letters. So we're fixing the random variable y at the value little y. Now, we're going to focus on discrete random variables in this video, but the math is pretty much identical for continuous random variables. You just replace any sums with definite integrals. Here's a more official definition. Suppose we have these two discrete random variables. The conditional probability mass function of x when y is fixed at some value, little y, is given by g of x given y is f of x comma y over f sub y of y, where f sub y of y is the marginal PMF of y evaluated at that particular value. Now, that's a bit of a mouthful, it's kind of ugly looking, but honestly, this is just a definition of conditional probability. If you take that marginal PMF from that denominator and move it over to the other side, you literally have the definition of conditional probability. Remember, f of x comma y is asking for the probability that the random variable x has the value little x, and the random variable y has the value little y. That's an AND statement. And that gets evaluated by finding the probability that y is equal to that value times the conditional probability that x has that value given that y has that value. Typically, G is used to denote the conditional probability where y is fixed, and H is used to denote the conditional probability where x is fixed. So the definition for H, where we're fixing x, is exactly the same, just with the roles of x and y reversed. I think all of this makes a lot more sense when we start doing an example. So here's an example. Here I have two random variables, x and y. They have a joint probability distribution that's given by this table. So for instance, the probability that x is 1 and y is 2 is 12%, 0.12. Notice that all of these probabilities add up to 1. This is a legitimate joint probability mass function. That is, f is a legit probability mass function. We want to compute first g of x given that y is 3. So what's the probability distribution for x when y is 3? So in order to do this, we're going to have to compute three different probabilities. We're going to have to compute the probability that x is 1, 2, and 3 when y is 3. Notice that the probability of x being 4 when y is 3 is going to be 0. That's just not possible. Using the definition, I'm going to compute f of 1 comma 3, the probability that x is 1 and y is 3, and I'm going to divide by the overall probability that y is 3. That is a marginal probability mass function. Overall, I get 0.10 divided by 0.10 plus 0.107 plus 0.11. So I'm taking the individual value, that 0.10 here, and dividing by the total probability that's available to us in the column y equals 3. And in this case, overall, we get about 35.7%. Similarly, we can do the conditional probability that x is 2 when y is 3 to get 25%. And we can do the probability that x is 3 when y is 3 to get 39.3%. I encourage you to pause the video at this point to do those calculations and check that you're getting the same answers as me without just watching what I'm doing. In summary, the conditional probability mass function for x when y is equal to 3 is given with this table. Here we have those probabilities for x being 1, 2, and 3 when we already know that y is equal to 3. Notice that these sum up to 100%. A conditional probability mass function is always a probability mass function in its own right. I'm going to do the conditional probability for y given that x is equal to 3 a little bit faster. Again, I encourage you to pause the video here and try and do those on your own before watching what I do. We are going to need to compute the probability that x is equal to 3 and y is some value little y, divided by the marginal probability that x is equal to 3 for y is equal to 1, 2, and 3. So we're going to be looking at the x equals 3 row of this table. That row has a total sum of 0.27. So what I'm going to do is I'm going to take f of 3 comma y divided by 0.27 for the three different values of f of 3 comma y. And that gives us this table that arithmetic simplifies out to give us h of 1 comma 3 is 7.4%, h of 2 comma 3 is 51.9%, and h of 3 comma 3 is 40.7%. Conditional means, variances, and standard deviations are computed kind of in the obvious way. Remember, when you're doing a conditional distribution, you're taking one of the variables into account by assuming that it's fixed, being left with a single variable probability mass function. And so the formulas I'm about to flash are just saying that exactly. Find the expected value or variance for that probability mass function. The expected value of x given y, sometimes denoted mu sub x vertical bar y, is the sum over all the possible x values of x times the probability of x given that y is equal to little y. Similarly, for variance, we have this formula, which simplifies out to a more practical formula that we usually use, the expected value of x squared, again for that fixed value of y, minus the expected value of x for that fixed value of y, quantity squared. Again, these are all just the regular single variable formulas applied to the variable x once the value of y has been fixed. Let's wrap up by computing the conditional mean and variance of x when y is equal to 3. And this is very direct because we already have the conditional distribution of x given by this table, g of x given 3. To compute the mean, we're going to take each of our possible values of x and multiply them by their respective probabilities. Add all those up. The expected value for x when y is 3 is going to be 2.04. For the variance, just using our basic formula, plugging in, doing the arithmetic, we get 0.75.